organic compounds. Yesterday we went through and we had a 5-carbon molecule in either single bond, double bond, triple bond, with an alcohol group, with a carboxylic acid group, with an ester group. The only one that I forgot to put up there was a halogen. And for whatever reason, it doesn't come into play. It does, but it doesn't. It's kind of weird. Anes are single bond, enes are double bonds, ines are triple bonds, alcohols. A halogen is denoted by an X. This is not something that we're familiar with because I don't write X's, I write what they actually are. But bromine, this would be the equivalent of bromine, chlorine, iodine, fluorine. Okay, that's what the X's are. That's group 17. Okay. Then we get the double bonded OOH is a carboxylic acid, and a double bonded O2 and O bonded to another carbon chain. That's an ester. These two pieces here typically, nope, that's not what I want to say. Not here. That one there. An ester, even though it's not shaped like this, remember this shape here? What do we call this guy? Benzene. This guy and this esters are typically aromatics. Aromatic specifically belongs to this group of carbons with cyclical with alternating double bonds, 6 carbon chains specifically. But esters have a scent to them. This is awesome. It's coming back up. Give the computer 2 seconds. Whoa. It's too dark. Okay. So what the rest of these guys are called is aliphatic. Okay. Riley, move up closer if you can't see from back there. After that, this is where we put the 5 different compounds on there. And we did double bonds, single bonds, triple bonds, esters, alcohols, and carboxylic acids. And we had a guessing game of what we thought would be a highest boiling point or a lowest boiling point. When we say highest boiling point, this requires the most energy, and this requires the least energy. Okay. And we were all like somewhat close when we look at the shapes. Double bonded O to an OH. This one here is C bonded to an OH. And this one here is C bonded to an O bonded to a C prime group. This is a C with a triple bond. This is C with a single bond. And this is C with a double bond. These 3 here are because of this hydroxyl group. And there was a hydroxyl group here, right? An ester is the combination of an acid, and an alcohol. So this also does have the H on it. And when we remember back from Chem 20 on the hydrogen bondings, that was F, O, and N.
What is the OH
It's, you missed that lesson, but it's the R bonded to the O. It had an alcohol group on it. and the H off of the carboxylic acid binds with the alcohol group, creates water, and you get an ester. Okay? So that's why these require the most amount of energy. And then as we break down, it takes energy to break the 3 bonds, the single bond, and the double bond. Now, I don't have a full understanding of why a single bond requires more energy than a double bond. I'm having to think it's something to do with the level of saturation. But I don't have a 100% answer. And when you go through the textbook, it neither has a 100% answer. Okay? It just expects you to know that. This piece here, if I had this piece, this is how many carbons? And we would call this what? Bless you. What would I call this guy? It also has 6 carbons. And so then these two pieces here, simple cyclic compounds, are similar to those of aliphatic. Remember aliphatic here? Hydrocarbons having the same number of carbons. This is 6 carbons, this is 6 carbons. Okay?
Isn't benzene always going to be a cyclohexane?
Nope, because a cyclohexane means that there's only single bonds in there.
Oh, because there can be.
Yeah. Okay. When we're comparing organic compounds within the same functional group, okay, so either they're all anes, they're all enes, they're all the same type of group, we call that a homologous series. The longer the hydrocarbon chain, the greater the boiling point due to London dispersion forces. Remember, London dispersion were the weakest, but because it's a molecular compound, it's carbons and hydrogens, and it's carbons attracted to carbons, the longer the chain, the greater the boiling point, because there's more of those bonds to break. It requires more energy. So if we were to look at all alkanes, and we can see that here because they're all ending in A-N-E. So this is ethane is how many carbons? Propanes, butanes, pentanes, and hexanes. Okay, so it says the longer the hydrocarbon chain, the greater the boiling point, right? Ethane looks like this, propane like that, that's butane, that's pentane, that's hexane. We can see that it takes more energy to break this guy apart. This is below freezing. This is minus 89 degrees Celsius. Here, this is plus 70 degrees Celsius. This takes nothing. This is a gas at 0 degrees Celsius. This is still a liquid. Do you see how I'm reading that? Okay, if I let's look at double bonds, ethenes, propenes, butenes. This makes it the homologous series, the fact that they're all double bonds. If I look ethene, which is only 2 carbons, its boiling point, its transition from a liquid to a gas is at minus 104.
So it's got to increase by 104 to turn into a gas.
No, at minus 104, it will go from a liquid into a gas. So at 0 degrees Celsius, what we call freezing for water, it's already a gas. Hexene, which is a liquid that we use, boils at 63 degrees Celsius. Let's look back here. This is something that we're all familiar with, propane. Minus 42 is when it boils. So how do you take that propane tank, go and get it filled at the local gas station and put it on your barbecue? Because it's a liquid when they put it in your tank.
The barbecues obviously have a cooling agent.
Oh, you think it has a cooling agent? Go back to Chem 20. PV equals nRT. PV equals nRT. So as pressure goes up, the temperature will go up. So if we increase the pressure, we can leave that as a liquid.
So then you got decrease.
Pardon me?
When you're at the very end of the
Yeah. So you can actually take a full disclaimer, do not do this. I do not say that Mrs. Pryor told you could do this. But you can take a lit match and put it in full-on liquid propane. As long as there's no headspace above it, as long as there's no room for vapors. Because it's the vapors that ignite, not the liquid itself. Where do we have liquid propane at? Below minus 42. So that tank is under pressure. You're not sticking a lit match in there because you cannot guarantee that there isn't a little bit of space above it where all those fumes are gathering. Okay? All right. Propane, ethane, butane, again, another homologous series. So you can see the more carbons we have, the boiling point is increasing. When we are looking at a homologous series, it's the same formula. We could look at here, this is methanoic acid, ethanoic acid, propanoic, butanoic, pentanoic. This one here is CnH2n 2 plus 2. So this is methane, ethane, propane, butane, pentane. Okay? Now, even though a lot of these up here were all gases at room temperature, we can see if they're soluble. We talked about this in Chem 20. Are molecular compounds soluble in water? Some are, but is oil soluble in water? Soil is a long chain hydrocarbon. So we can see here, if it's nonpolar, it's not soluble in water. What makes a hydrocarbon polar? The hydroxide group or the oxygen group on there makes it polar. So, does an ester become soluble if it's less than 4 carbons? Is an alcohol soluble in water? Yeah. Stop and think about your recreational habits on the weekend. Can you mix it with pop? Yeah? You don't get a separation of layer. You don't get a vodka layer. You don't get a pop layer, right? They mix. It's polar. You what? You don't know, you don't drink. Because we're being recorded, so you're being honest. Okay. Yeah. A carboxylic acid has that group. It has that OH group in there, that polar piece. So yes, it's soluble. Does an alkane have a hydroxyl group on it? No. You got to have an alcohol group, a carboxylic acid group, and if it's butane and lower, you can be an ester.
if it had a hydroxide, that would just become alcohol.
Exactly.
So then what